Hello everyone, this is our official Sando. Today I'm excited to introduce a new series to prepare for AI domain interview. So this series will cover a few hot topics in AI domain interview. So the way I make the series is I first will introduce the fundamental of those topics and come up with frequently interviews questions explanations. So today I'm going to cover the topic in estimation domain. Then I'm going through the MLE and MLP by following. As the videos I did for coding interviews, I will also make a separate Google Sheet to summary all the videos I made for AI domain. So you can find the list in video description. If you like my videos, please support me by subscribing my channel. Before going to MLE and MAP, I want to introduce some fundamental for Gaussian and normal distribution first. So the Gaussian distribution tells us what's the probability of an event happens. So for these plots, I plot a Gaussian distribution. In the x-axis, it shows a larger number of events, and in the y-axis, it denotes the probability of the current event will happens. Here we define the integral of the probability of the event. The event came from minus infinity to infinite. The sum of them will be 1, which means some of this group event will definitely appear, and the sum of the probabilities of the order those events happens will be 1. So in the above equations, this is the probability distributed functions for Gaussian distributions. So it formalized by a normalizer multiplied the exponential functions of a quadratic. The Gaussian distribution can be modeled by mean and standard deviation square, which we call the variance. Why people like Gaussian distribution a lot? Why they want to modeling the process in a lot of domain? The first reason is that it follows by the central limit theorems. So the theorems tell us if we sample a bunch of random numbers from a lot of arbitrary distributions, if we add them together, we get approximately the Gaussian distributed. So that in our real process, if a process can be considered by a few sub process, so those sub process can be modeled by any arbitrary distribution. But if we glue them together to get a main process, it's mostly like a Gaussians. So this is why we want to model the process as a Gaussian distributions. Its second advantage is that it makes math simpler. If we take a log of the PDA functions, so the exponential cancel out, eventually we get the quadratic. So the quadratics makes a lot of things easier. You probably can see in the later examples. The third point is that interdistribution is only described by mean and variance, as I mentioned earlier. Okay, so then what's the MLE? MLE is the maximum likelihood estimation. The likelihood function is represented by a conditional probabilities. This conditional probabilities means if we know the true value is theta, what's the probabilities we obtain the measurements? Then if we give observation z and the likelihood functions, we can calculate the true value thetas by find the value theta, maximize likelihood functions. Okay, then the question time. If we have two independent sensor measurement from same sensor, Z1 and Z2, for example, temperature sensors to measure the temperature, then what's the sensor arrows can all be modeled as a Gaussian distributions. So we want to estimate value x. You can pause here for a few minutes, try to work on solution. Then here are the solutions. We solve this problem by MLE. So first, we formalize likelihood functions by using drawing probability. Then the drawing probability also can be rewrite by these two conditional probabilities multiplication because those two measurements are independent. Since the error modeling is Gaussian for both conditional probabilities, our likelihood functions is asymptotically equal to 2 PDF of Gaussians. Next, we combine these two Gaussians. Remember that we want to maximize likelihood function in MLE. Actually, it's asymptotic equal to minimize the minus ln function. Do you still remember the feature for Gaussian distribution? It says if we learn the Gaussian distributions, we can obtain the quadratic function for two frames. Then we expand all the functions, we obtain another quadratic-like representation. Of course, for simplicity, we always want to formulate quadratics, and here we plus some constant parameters here. To finish the MLEs, we want to find the x to minimize the minus ln likelihood functions. The way to find the minimized functions is always used to take the derivative of this one above x. Then the quadratic function can be rewritten as 2x minus x bar divided by theta square. We want to make this equation to 0 to find x to that one. Of course, the best x here is equal to x bar, which is z1 plus z2 divided by 2. It makes sense, right? So if we want to do the first guess, if you don't know these MLE tricks, of course you will guess it will be the average of two measurements because two measurements are follow the same error distribution. So if you look more deeper, actually its likelihood functions is Gaussian, right? Because the minus ln likelihood for each measurement is quadratic. So right now our new ln likelihood is another quadratic. So eventually actually we can model the best estimate as another Gaussians. So actually it's also z1 plus z2 divided by 2 based on the quadratic here. Then in other words, it's demonstrate our previous MLE result makes sense. Then what's MAP? So MAP is another estimations technique to estimate the values by given the measurement. Basically, it's defined as if we given a measurements, then what's the probabilities of our best estimations? So again, we want to find the best estimation here to maximize our probability here. For remissions, we have a conditional probability rule here. If we have two independent event, its joint probability is the conditional probabilities multiply its own probabilities. We can written as another way by conditions theta of z multiply p theta. Based on these conditional probabilities equations, we obtain the Bayes theory. So basically, we just put pz here in another side of the equation. So we obtain the Bayes theory. So Bayes theory is used to doing the maximum posterior estimation. Since the normalized part here is not related to the thetas, we want to maximum our posterior probabilities. So we can ignore this part. So eventually, these conditional probabilities can be written as pz theta multiply p theta. I will illustrate how we use this part in later question. Okay, here comes the question time. If we have an estimation theta bar of temperature sensor at last timestamp, its error can be modeled as one Gaussian at theta bar and the ib theta bar. We also have another sensor measurement z coming in these times. It can be modeled another Gaussian as theta z ib theta z square. The question is asked to estimate theta at current timestamp. Please pause for a few minutes and work on your own solution. Okay, so the solution is to use MAP. So first we have our Bayes theorem. It's a likelihood function multiply prior probabilities. So the likelihood given the best estimations, what's the measurement probability will be? The measurement will be basically the second Gaussian distribution. And the prior is our previous estimation probabilities is followed by another Gaussian. As what we did in problem 1, we do the minus logarithm of our posterior probability here. It ends up, of course, to quadratic function. Then we expand two quadratics and combine them together. We obtain two parts. First part is formulated by standard deviation. Another part become very easy. It's another quadratic. Then it's a theta equal to minus ib theta minus square theta z plus ib theta bar minus square multiply theta bar divided by two distributions. So to calculate the minimize of the minus log is very easy in this part, right? First part, this is a constant. It's not related to theta. And second part is a quadratic. It's also greater or equal to 0. So the minimize this one is equal to 0, which is equal to theta equal to the second part. So naturally here we obtain our best estimation of thetas equal to the second part here. One thing interesting to denote here, this is the same solution if we change questions definition a little bit. The way to change that is the two Gaussian distribution is all given for two separate measurement as in the previous question. So previous question, we have two measurements all followed by the same Gaussian distribution. So what if we change that for two measurements followed by two Gaussian distribution? Actually, eventually the MLE of theta will be the same result as we obtain here. I don't want to go deeper for that part. You can feel free to practice that. Then this finding is show the connection of MLE and the MAP, so that MAP basically we take the prior as another sensor measurement by follow another Gaussian distribution, and for the whole process to obtain the best estimate is the same of MLE. So basically MLP you just put all the additional informations to the total estimation. Then okay, yeah, that's all I want to talk today. Hope you like this series, and please provide comments and what you think below in these videos. Then see you in next videos. Bye.